Hi everyone, this is the first video for day 2 of the chapter 8 lectures. Just a reminder, make sure that you're doing your readings as we move forward and as you watch the videos and attempt all of the homework. I want to try something a little bit different today with regards to the pre-class. I want us to try to put our questions and answers for today's pre-class on a discussion board. So if you have to fulfill your weekly quota of comments or questions, then feel free to head on over to that discussion board and post your question or your answer. Here's what we'll be talking about today. We'll review what we talked about last time. I want to introduce you to the phase rule. Then we'll get to a couple of different types of phase diagrams that incorporate pressure and volume in addition to temperature. Then we'll hit the Clapeyron equation and then extend that to the Clausius-Clapeyron equation. Last time we saw how the phase depends on the temperature. So for instance, if we have temperature down here and chemical potential there, the solid phase had a curve like this, the liquid phase had a curve like this, and then the gas phase had a curve like this. And the system always chose whichever curve had the lowest chemical potential for that region. And the slopes of these curves all depend on the entropies of the different phases. Similarly, we also saw how the chemical potential changes with pressure. For instance, the gas phase had a curve like this, the liquid phase had a curve like this, and the solid phase had a curve like this. And so each of these intersection points represents a change in the phase. So as we increase the pressure, in most cases we're shifting from the gas to the liquid to the solid state, though if the molar volume of the liquid is less than the molar volume of the solid, like in the case for H2O, then we'll shift from gas to solid and then to liquid. Okay, we also we reviewed pressure, temperature, phase diagrams, which tells us the phase for a given combination of temperature and pressure. Remember from previous chapters and previous courses that if we have a coexistence between a gas and a liquid state within a system, then there's going to be a pressure of that gas above the liquid, and we would call that the vapor pressure, and that primarily depends on temperature. We saw in the case of increasing pressure, we saw an interesting shift in the boiling point as a result of the increase in pressure, and that's because we're increasing the chemical potential substantially for the gas phase, but not increasing it all that much for the liquid phase. And so now the new intersection between the chemical potentials of the different phases has increased. So we actually have an increased boiling point than we would at a lower pressure. And then depending on the molar volume of the solid phase, we may get a raising or a lowering of the freezing point. And if we depending on the molar volume of the liquid versus the solid state, we may get a freezing point elevation or a freezing point depression. We also saw how we can have multiple solid phases, for instance, diamond versus graphite, or ice 1 versus ice 9, or our favorite, chocolate 5 versus the other phases of chocolate, which taste nasty. And by the way, it's not just solid phases. There can also be multiple liquid phases. Okay, moving on to the phase rule. The best way to understand the phase rule is that F corresponds to the degrees of freedom, which is just a fancy way of saying ways we can move around a pressure-temperature phase diagram or any other kind of phase diagram. And P represents the number of phases. So imagine if we have a surface along which we can freely move like so. Notice that we have two different ways that we can move. We can move up or down, or left or right, or any combination of those. So therefore, our F is going to equal 2. There's 2 degrees of freedom, 2 ways we can move. If we only have one way that we can move, say along a straight line, then that means there's only 1 degree of freedom. And if we have no way that we can move, we're stuck at a particular point, then we have 0 degrees of freedom. So what does this imply? This implies that P has to equal 1 in this particular case, because 3 minus 1 equals 2. So that means only one phase can exist if we have 2 degrees of freedom, and we can move freely around the phase diagram in 2 different directions. If we're constrained to a line, in the case of F equals 1, then that just means that 2 phases will exist. Maybe this is on a coexistence curve of a pressure-temperature phase diagram. So the solid and the gas phase are coexisting, for instance. And then, of course, if we have a particular point on the phase diagram, then potentially 3 different phases can exist, like, say, at the triple point. Okay, here I'm depicting a different kind of a phase diagram, a pressure-volume phase diagram. By the way, specific volume just means molar volume, Vm. This one looks a lot different than the pressure-temperature phase diagram. It's quite a bit more complicated. That's because they are no longer coexistence curves on this phase diagram. There are coexistence regions. So as you can see, instead of having a liquid-vapor coexistence line, we've got a liquid-vapor coexistence region. So if we choose a point for a specific molar volume and add a specific pressure, then it's not along a line, but we can change the molar volume, and that's going to change the proportion of liquid versus vapor, but they're still going to be coexisting, at least until we move past one of these lines. In a similar vein, we have here on this slide a pressure volume temperature phase diagram. And we saw this in our first lab, so it should be fairly familiar, but I want to draw your attention to the fact that this pressure volume temperature phase diagram is interesting because when looked at from this direction, you've got a PT phase diagram, but when looked at from this direction, you've got a PV phase diagram. So looked at from this direction here, it should look very similar to the one on the last slide. And when looked at from this direction straight on, you see that the coexistence regions just look like a straight line because we're looking straight at it from the edge. And that's what the PT phase diagram looks like. But that's only because it's from that particular perspective. Next, I want to introduce you to the Clapeyron equation. And the Clapeyron equation is pretty interesting because think back to a pressure-temperature phase diagram. It looks something like this. There's the triple point, then there's the critical point, and then there's the coexistence curve. Down here we've got the gas phase, solid phase up there, liquid phase right up there. Maybe you've wondered, what's the function that describes these particular coexistence curves? Well, today is your lucky day because that's what you get to find out next. Or more specifically, what's going to be the slope at particular points along these coexistence curves. That's what the Clapeyron equation is going to tell us. And it all begins by recognizing that the chemical potential of a particular phase, say phase 1, must equal the chemical potential of a different phase if the 2 phases are coexisting. Sort of like when we saw a plot of the chemical potential versus temperature, the phases were coexisting when those 2 curves exactly matched up with each other. And another way to write this for a pure system is that the molar Gibbs free energy of phase 1 is equal to the molar Gibbs free energy of phase 2. But instead of writing phase 1 and phase 2, I'm just going to simplify this by doing alpha and beta. All right? Now, if the chemical potentials or the molar Gibbs free energies are equal to each other, then along this coexistence curve, any tiny change in the molar Gibbs free energy is going to be equal between the two phases. The molar Gibbs free energies of alpha and beta are going to be equal. That's so that we stay on that coexistence line. The next step is I want to remind you what is the total differential for the Gibbs free energy. And if you recall, it's equal to the negative entropy times a change in temperature plus a volume times a change in pressure. And you can find that using the thermodynamic square. And I'm just going to make a slight modification here by including molar quantities so that we can use this one directly. So now I can just take this total differential and plug it into those two expressions right there, and I get negative Sm alpha dt. We're assuming that the temperature is going to be the same for the two phases. Molar volume of alpha dP. We'll assume that the pressure is the same for the two phases. Sm beta dt. Vm beta dP. Right, so now we want to get the D and the P on the same side of the equation, and we want to get the S and the V on the opposite side of the equation. So I'm going to skip ahead. I'm going to do all that algebra now and skip ahead, and you can take a look back and see how I did it. Okay, so I skipped ahead and did some algebra. If you want to go back and walk through the steps, you're welcome to. I just wanted to address a step that I'm taking right now. I'm calling delta Sm as the difference between the entropies of the two phases and delta Vm as the difference in the molar volumes of the two phases. And now I'm going to continue my algebra from here. Okay, so I finished all the algebra. Feel free to go back and walk through it step by step yourself if you would like to, but this is the final result. This here is the Clapeyron equation. And it tells us for a particular place in the pressure temperature phase diagram, what the slope is going to be. So say we knew the molar volume and the entropy for that point right there. Let me use a different color. For that point right there, if we knew the delta Sm and the delta Vm, then we could exactly find the slope of that point right there. And so in your homework, you'll be given the delta S and the delta V of certain points along that coexistence, or you'll have to calculate it and then get the slope of that particular line. Or I suppose it's possible you may have a problem where you're given that slope and then you find one variable or the other.